Welcome back, design junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Always appreciate the support, yeah.
So, usually when we talk about engineering with the general public, there is this prevailing expectation of absolute infallible precision.
Oh, for sure. It's treated almost like a medical diagnosis.
Exactly. Like you break your arm, right? The X-ray shows that jagged white line on the bone, and the doctor just points at it and says, there it is, that is the problem.
Right. It's viewed as completely binary. The bone is either broken or it is not broken. It's just a clean, observable fact.
And, it is incredibly comforting to think that way. As human beings, we like things to be visible. We like them to be perfectly categorized.
And it makes us feel safe.
Yeah, exactly. We want to believe that when we sit down to design a complex machine, like a drone or a car suspension or a rocket nozzle, the mathematics will just give us this absolute infallible blueprint that perfectly mirrors reality.
Which is a nice thought.
But then you step into the actual physical world of dynamic systems. You step into this chaotic, real-world mess of mechanical, electrical, and fluid engineering. And suddenly, well, that X-ray machine is broken.
The blueprint lies to you.
It totally lies. We are looking at a design landscape that is, to put it bluntly, incredibly murky.
It is the absolute definition of diagnostic muddy waters. And, that is exactly why we are pulling from a incredibly comprehensive manual for today's deep dive.
Right, the manual on mathematical models.
Yeah, Mathematical Daughters of Dynamic Physical Systems. It is a dense, rigorous, and, completely essential breakdown of how we actually model systems that move, change, and react over time.
Because if you don't understand the modeling, you really don't understand the system.
Exactly.
Okay, so let's unpack this right out of the gate, because our mission for you today, listening to this, is exploring the ultimate pain point in mechanical engineering.
The nightmare scenario.
Right, the nightmare scenario. Building physical systems that just vibrate to pieces or overheat or simply fail the very second they leave the CAD software and enter the physical world.
Which happens way more often than people think.
Oh, all the time. And why does this happen? Usually it's because the mathematical models driving the design were completely misunderstood from day one.
From the very beginning, yeah.
So today, we aren't just memorizing equations. We are breaking down the massive misconceptions that screw up designs.
We're going to walk through step-by-step fixes.
And we are showing how to actually optimize a system before you spend a single cent on physical prototypes.
And what's really fascinating here is the sheer cost of ignoring this foundational step. Formulating mathematical models of dynamic systems isn't just some academic exercise that your professors force you to do.
It feels like it when you're in school, though.
Oh, definitely. But in the real world, mathematical modeling is significantly less costly, incredibly less dangerous, and fundamentally faster than building real-world test rigs.
A good model lets you answer what-if questions that current technology might not even be able to realize yet.
Exactly. You can test a spacecraft's thermal limits as it re-enters the atmosphere.
Without ever launching a rocket.
Right. You can test a submarine's crush depth without drowning a crew.
Yeah.
But the massive, unforgiving catch is that you have to model it correctly.
And here's where we hit the very first trap that ruins so many projects. I like to call it the build it first trap, mixed heavily with the simplicity misconception.
Oh, the simplicity misconception is a big one.
It's a massive real-world issue. Engineers, especially, junior ones with access to incredibly powerful software, they assume that the absolute best model is always the most precise, most complex one you can possibly create.
You see this all the time. They just throw every single variable into the simulation.
Right. They are modeling the wind resistance, the micro-friction of a single ball bearing, the ambient humidity.
Probably the gravitational pull of the moon, too.
Literally. And they assume that because it is complex, it is good engineering.
But if we connect this to the bigger picture, that instinct is completely backward. It fundamentally misunderstands the purpose of a model.
Oh, so?
Well, this brings us to the core modeling trade-off: fidelity versus effort. A highly complex model requires zero assumptions, right? It attempts to map reality almost perfectly.
Which sounds good on paper.
It does. Yeah. But here is the problem. A model that complex cannot be solved analytically. The math just becomes too tangled, too nonlinear, too heavy.
So the computer just chokes on it.
Exactly. It must be simulated experimentally by a computer, which takes enormous computing power, endless time, and honestly, it introduces entirely new avenues for digital errors.
Wow. Okay.
Because the actual best engineering model is not the most precise one. The best model is simply the most basic, simple model that yields the exact information you need to make a specific design decision.
I want to make sure you, the listener, really internalize this because what does this actually mean for your workflow?
It means you have to adopt a strict iterative loop.
Okay, step one.
Step 1. You start by formulating a drastically simplified mathematical model.
Keep it super simple.
Right. Step 2. You translate that simple model to computer code. Step 3. You simplify and linearize it even further to understand its core behavior.
Wait, further?
Yeah, strip it down. Then step 4. You analyze that model, and then, and only then, do you simulate a slightly more complex version to test alternative designs.
And finally, you implement the control system.
You got it. That's the loop.
But wait, let me push back on this because I can hear the skeptics right now. Isn't engineering supposed to be an exact science?
People love to say that.
Right. If you build a quote-unquote simple model of a car suspension, let's say you intentionally ignore the complex friction of the rubber seals inside the shock absorber, aren't you just lying to yourself about how the car actually drives?
That's a fair point.
I mean, if you ignore reality, won't reality bite you when you actually build the car?
It raises an important question, but no, you aren't lying to yourself. You are isolating the variables that actually matter for the specific problem you are trying to solve right now.
Okay, give me an example.
Think about the car suspension you just mentioned. If your immediate goal is simply to determine the required spring stiffness to keep the car's chassis from bottoming out when it hits a standard speed bump at 30 miles per hour.
Just a standard suspension check.
Right. You absolutely do not need to model the thermal expansion of the damper fluid over a 4-hour road trip.
Ah, okay.
The thermal expansion is real, yes. The rubber seal friction is real. But their impact on the specific question of will the car bottom out on this bump is mathematically negligible.
So they just don't matter for that specific test.
Exactly. You add complexity only when the simple model fails to answer the question or, when you move to the next phase of design where thermal dynamics actually matter.
Okay, that makes perfect sense. You strip away the noise to see the signal. But to build these simple models without getting completely lost in the math, you really need a universal language.
You absolutely do.
Because let's face it, if you look under the hood of an electric vehicle today, modern systems aren't just mechanical anymore. They aren't just simple gears and levers.
No, not at all. They are an absolute multi-domain mess. Modern engineering is completely mechatronic. You are dealing with systems that are part mechanical, part electrical, part fluid, and part thermal, and they're all interacting simultaneously.
Which sounds like a nightmare for the math.
It is. If you treat each domain with completely different math, like if your mechanical engineers are using one set of equations and your electrical engineers are using another.
And your fluid dynamicists are off in their own world using a third set.
Exactly. You create these massive, paralyzing bottlenecks in your design process.
Because nobody can actually talk to each other. The electrical guy says the battery voltage is dropping, and the mechanical guy says the motor torque is failing, and they literally can't mathematically link the two in a single equation.
Precisely. And the elegant solution to this multi-domain mess is to unify the physics entirely using something called ideal elements.
Ideal elements. Okay, let's get into this.
So in system dynamics, we can boil almost all of physical reality down to two primary physical variables. We call them through variables, which we denote as F, and across variables, which we denote as V.
Okay, let's slow down and really define these, because this is basically the Rosetta Stone for understanding complex engineering.
It really is.
Through variables are exactly what they sound like. They are quantities that are physically transmitted through an element.
Right.
Like if I push on a spring, the mechanical force transmitted through that spring is a through variable. In an electrical circuit, the current flowing through a wire or a resistor is a through variable.
And in a hydraulic system, the volume of fluid flowing through a pipe is a through variable. In a thermal system, the heat flowing through a conductor, also a through variable.
So that's the F, and then we have the across variables, the V.
Right. These are the differences measured across the terminals or the boundaries of the element.
So if you have a mechanical damper, the velocity difference between the top of the damper and the bottom of the damper is your across variable.
Yes, and in an electrical system, it would be the voltage difference across a battery's positive and negative terminals.
Okay, and for fluid?
In a fluid system, the pressure drop from the entrance of a pipe to the exit is the across variable. And in a thermal system, it's the temperature difference across an insulated wall.
Here is where it gets absolutely incredible for me. Power-like. The actual tangible flow of energy into an element is universally defined across all these domains using these exact two variables.
It's beautifully simple. Power is simply the product of the through variable and the across variable.
You can read the universal equation as power equals F multiplied by the difference between V2 and V1.
Exactly.
It literally does not matter if you are designing a mechanical gear train, an electrical circuit, or a hydraulic press. The math for power is identical.
Which is incredibly elegant. It means a mechanical engineer and an electrical engineer are actually speaking the exact same language, just using different physical mediums.
That is so cool.
And using these unified variables, we can categorize all passive energy elements in the universe into three specific types.
Okay, what's the first one?
First, we have T-type elements, or inductive storage elements. These are components that store energy based on the through variable.
Like what?
Think of a mechanical spring storing force, or electrical inductance storing current in a magnetic field, or fluid inertance storing momentum in a moving column of water.
Okay, so T-type elements bank energy based on what is flowing through them. What is the second type?
The second is A-type elements, or capacitive storage elements. These store energy by virtue of the across variable.
So measuring across the boundaries?
Right. This includes physical mechanical masses storing kinetic energy due to a velocity difference, electrical capacitance storing charge due to a voltage difference.
Fluid capacitance, like a water tank storing energy due to pressure.
Exactly. And thermal capacitance storing heat. But there is a very critical note here for mechanical systems. A mass must always be referenced to an inertial, non-accelerating frame.
Meaning its zero velocity reference is the ground.
Yes.
Right, because you can't measure the kinetic energy of a moving mass without knowing what it's moving relative to. I mean, if I'm holding a bowling ball on a moving train, the ball's kinetic energy relative to me is zero.
But relative to the ground outside, it's massive.
Exactly. You have to anchor the across variable to a non-moving ground.
That's a great way to picture it.
And then we have the third type, the D-type elements. These are the dissipators.
Right, they don't store energy at all. They destroy it. Well, technically, they burn it off as heat.
So mechanical dampers, electrical resistors, fluid friction in a pipe.
Yeah. Power always flows into a D-type element. It never, ever gives power back to the system.
A spring will bounce back, a capacitor will discharge, but a resistor just gets hot.
Exactly. And beyond those three passive storage and dissipation elements, we also have multi-port elements that connect different parts of a system together.
Like transformers.
Right. Transformers like mechanical levers, gear trains, or electrical transformers, they scale the variables up or down while maintaining power.
And gyrators.
Gyrators like gyroscopes or certain electrical components, they cross-link the variables. They actually link a cross variable at one port to a through variable at the other.
Oh, that's wild.
And finally, transducers, like an electric motor, which literally convert energy from one physical medium, like electrical current, directly into another, like mechanical rotation.
I feel like this is such a massive unlock for anyone listening who struggles to conceptualize different fields of engineering.
It really bridges the gap.
If you are struggling with a complex fluid piping system, you can literally draw it out and look at it like an electrical circuit. Water flow is your electrical current. That's the through variable.
The pressure drop in the water is your voltage. That's the across variable.
A narrow section of pipe is just a resistor. A large water storage tank is just a capacitor. They speak the exact same mathematical language.
That is the beauty of ideal elements. You can translate any physical system into a unified network. But, and this is big, but knowing the individual elements is only half the battle.
Right. You have to actually wire them up.
Now that you have these unified pieces, you have to connect them together to build a complete system without breaking the fundamental laws of physics.
Which brings us seamlessly into the problem of wiring the system together and trying to escape what I like to call the infamous black box of engineering.
Oh, the black box, yeah. System structure and interconnection are governed by two vital, unbreakable laws. First, we have continuity equations.
What do those say?
This law states that the algebraic sum of all through variables entering any specific node or junction in your system must equal zero.
So in classical mechanics, this is dynamic equilibrium, or basically Newton's laws of motion.
Right. And in electronics, it's Kirchhoff's current law. The logic is simple. You cannot magically create or destroy force, current, or fluid at a junction. What flows in must flow out.
So if three pipes meet at a joint, the gallons per minute flowing into the joint must perfectly match the gallons per minute flowing out. The node itself can't store water.
Exactly. And what is the second law?
The second law deals with the compatibility equations.
Right. This states that the algebraic sum of the domains across variable differences around any closed path or loop in the system must equal 0.
Okay, break that down.
It simply means that distance or voltage or pressure is a scalar quantity tied to physical space. If you start at one specific point in your system, trace a path around a loop through various components, and come back to the exact same starting point.
Your net change has to be 0.
Your net change in elevation, or your net change in voltage, or your net change in pressure absolutely has to be 0.
Because you can't walk around a staircase in a square and somehow end up higher than where you started unless you're in some M.C. Escher painting.
Exactly.
Okay, so you have your T, A, and D components. You have your node and loop equations based on continuity and compatibility. You sit down and you start doing the math.
And this is where it usually goes off the rails.
Yes, this is the massive pain point engineers run into. For decades, engineers relied entirely on the classic input-output form, the I/O form.
They treat the entire system like a mysterious black box.
Right, where an input goes in, some mathematical magic happens inside the box, and an output comes out governed by some terrifying, massive nth-order differential equation.
The black box approach is honestly a relic of classical control theory. It works for very simple things, but it fundamentally hides the internal reality of your system.
So how do we optimize this? What's the modern approach?
The optimization here, the way modern engineering is actually done, is moving entirely to the state variable form.
State variable form.
Yeah, instead of writing one massive, unwieldy equation linking the input to the output, modern control analysis breaks the system down into a set of state variables.
Which we label as x1, x2, up to xn.
Right. And these variables represent the absolute minimum number of independent variables needed to define the total energy state of the system at any given moment in time.
Okay, I need to act as the surrogate for the audience here, because if we just start throwing around terms like state variables and vector matrices, eyes are going to glaze over.
Fair enough. Let's ground it.
Let's make this highly visual and step-by-step. If I'm building a drone, how do I actually find these state variables? What do I look for?
It is actually beautifully intuitive once you know what to look for. You derive the natural state variables by simply counting your independent energy storage elements.
Wait, that's it?
That's it. Remember the T-type and A-type elements we just talked about?
The springs, the masses, the capacitors.
Yeah, exactly. For every independent T-type storage element, like a spring in your drone's landing gear, you write one equation for its shoe through variable of the force. Okay. For every independent A-type storage element, like the physical mass of the drone itself, you write one equation for its together. Cross variable its velocity.
Try to just link those up.
You solve your continuity and compatibility equations to link them all together, and you formulate the entire system into a compact, standardized set of vector matrices known universally as the A, B, C, and D matrices.
Whoa, back up right there. I know what a matrix is in standard math. It's basically an array of numbers.
Right.
But when you say A, B, C, and D matrices in this context, what are these 4 specific boxes actually doing? Like if I'm looking at the code for my drone, what goes into the A matrix versus the B matrix?
That is a crucial distinction. The A matrix is the system matrix. It defines the internal physics of the drone itself, completely independent of the outside world.
So it's just the drone's body.
Yes. It maps how the drone's mass interacts with its own structural stiffness and damping. If you drop the drone out of the sky with no motors running, the A matrix dictates how it falls and flexes.
Got it. And the B matrix?
The B matrix is the input matrix. It maps how your steering controls your motor thrusts, actually connect to and influence that internal physics.
Ah, so A is the physical body and B is the nervous system connecting the muscles to the body.
Exactly.
What about C and D?
The C matrix is the output matrix. It defines what your sensors can actually see.
Like the camera or the GPS.
Right. You might have a complex A matrix with 20 internal states, but if you only have a GPS and an altimeter on board, your C matrix maps those 20 states down to just position and height.
That makes total sense. And the D matrix?
Finally, the D matrix is the feed-forward matrix. It represents a direct bypass where the input instantly affects the output without going through the physical state dynamics first.
Which sounds rare.
It is. In most mechanical systems, the D matrix is just 0.
Okay, that makes it incredibly clear. But I have to play devil's advocate here for a second.
Go for it.
Why should a practical, hands-on engineer care about setting up these 4 state variable matrices?
It's a common question.
I mean, if the classical black box transfer function tells me that when I push the gas pedal down 1 inch, the car goes forward at 20 miles an hour, why do I need to know the internal energy state of the transmission gears? The car moves, the client is happy. Why do the matrices matter?
Because if you don't know the internal state, the system's behavior over time will completely blindside you.
Blindside me how?
Let's use your car example.
Mm.
Your black box equation simply says gas pedal input equals forward motion output. That's all it sees.
Right.
But what if, internally, your transmission is absorbing massive amounts of kinetic energy and heating up due to friction?
Oh, man.
The black box doesn't see the heat. It doesn't track the energy stored in the transmission fluid.
Yeah.
It just tells you the car is moving. Right up until the moment the transmission suddenly shatters into 1,000 pieces on the highway.
Wow.
State variables track every single pool of energy in the system simultaneously. They tell you not just what the output is doing, but whether the internal components are secretly ripping themselves apart.
That is a terrifying thought. The black box is basically driving blindfolded, just waiting to hit a wall.
Yep.
And that perfectly transitions us into the absolute nightmare of the time domain, because things don't just break instantly, they break over time. Energy builds up, oscillates, and tears things apart.
Exactly. But analyzing systems purely in the time domain using raw differential equations is incredibly painful.
The math gets nasty.
Very nasty. If you try to calculate how a mass bounces on a spring over 10 seconds using basic calculus, the math is horrific. So to deal with these time domain terrors, engineers use transform methods, specifically the Laplace transform.
The famous Laplace transform.
Right. The Laplace transform takes these horrific, tangled differential equations and turns them into simple, manageable algebra by moving the problem out of the time domain and into the complex frequency domain.
You know, I always like to explain the Laplace transform visually.
Well, let's hear it.
It is like trying to untangle a massive, knotted ball of yarn. That's your time domain differential equation. If you try to pull at the threads with raw calculus, it just gets tighter and more tangled.
It really does.
But a Laplace transform is like dropping that knotted ball into a magical chemical bath. The bath dissolves the knots entirely, and you are left with straight, parallel strings.
I like that.
You do simple addition and subtraction on those straight strings. That's the complex frequency domain algebra. And when you're done, you reverse the chemical process, pull the yarn out, and the math is solved.
Exactly. The output relies entirely on the system's transfer function, which we denote as h of s.
That's a perfect analogy. The Laplace transform untangles the dynamic behavior.
It really does. And when we look at how a system actually responds to a test input, like an impulse strike, a sudden step input, or a steady ramp up in force, we are really looking at two distinct phases of behavior.
What's the first phase?
First is the transient response, which is the initial, often chaotic reaction right after the system is disturbed.
Like the immediate bounce.
Right. Second is the steady-state response, which is how the system behaves after the initial chaos settles down.
So let's isolate these and look at first-order systems first. These
Yeah.
are the simplest dynamic systems.
Very simple. They only have one energy storage element, like a single mass sliding on a frictionless surface or a single capacitor charging.
Because there's only one storage element, energy can't bounce back and forth.
Exactly. The system's speed is governed by a single parameter called the time constant, which we denote with the Greek letter tau.
So what is the golden rule for engineers dealing with a first-order system?
The golden rule is incredibly practical. After 4 time constant, 4 times the value of tau, the system has reached roughly 98% of its final steady-state value.
So it's basically done moving.
For all practical engineering purposes, we consider it completely settled. It doesn't bounce, it doesn't overshoot. It is just a smooth, exponential curve flattening out.
But things get violently crazy when we step up to second-order systems.
Oh, yeah, they do.
This is where you have two energy storage elements trading energy back and forth, like a physical mass bouncing on a physical spring.
The spring pushes the mass gains kinetic energy, it overshoots, stretches the spring, and the spring pulls it back.
Now, the system's behavior is governed by two entirely new parameters: the damping ratio, called zeta, and the natural frequency, called omega n.
And this is exactly where physical systems vibrate to pieces. The value of the damping ratio, zeta, dictates absolutely everything about the system's survival.
Okay, let's walk through the zeta values.
If zeta is greater than 1, the system is what we call overdamped. It is sluggish.
Sluggish like what?
Imagine a door closer filled with thick molasses. It slowly, painfully creeps toward the closed position without ever slamming or bouncing past the frame.
Safe, but slow.
Right. Now, if zeta is exactly 1, It is critically damped.
I always say a critically damped system is like the perfect high-end kitchen drawer. You shove it as hard as you can and it glides inward incredibly fast, but it stops exactly at the end of the rail without slamming, clicking, or bouncing back even a millimeter.
Yes, exactly.
Yeah.
It is the theoretical ideal for a vast majority of mechanisms where you want speed without overshoot.
But what if zeta drops too low?
If zeta drops below 1, if it's between 0 and 1, the system is underdamped. It moves fast, but it overshoots the target, bounces back, and oscillates before eventually settling down.
Like a car with bad shocks going over a speed bump, it just keeps floating up and down.
Exactly. And if zeta equals exactly 0, you have no damping at all. You have pure harmonic oscillation. The system will literally bounce back and forth forever. It never settles.
And here's where it gets really interesting on the mathematical side. This real-world bouncing, this physical oscillation, is dictated mathematically by the location of complex poles in this plane.
Yes. When you solve the denominator of your transfer function, the roots of that characteristic equation are called the poles.
Okay, the poles.
If you plot these poles on a graph called the complex set plane, their physical location on the paper completely dictates whether the system will peacefully settle or vibrate itself to pieces.
So how do you read the graph?
The x-axis is real numbers, the axis is imaginary numbers. If your poles sit purely on the real axis, you get that smooth, sluggish, overdamped response.
Right.
But if the poles migrate off the real axis and become complex numbers with imaginary parts, that means the system is going to oscillate.
The imaginary part of the math literally translates to physical vibration in the real world. That is mind-blowing.
It is. And the closer those poles get to the vertical imaginary axis, the more violently and endlessly the system vibrates.
What if they cross it?
If the poles cross over to the right half of the plane, the system is fundamentally unstable. It doesn't just vibrate. The vibrations grow exponentially until the system destroys itself.
Like the Tacoma Narrows Bridge.
Yes. Think of that famous footage of the bridge twisting in the wind until it collapsed. That is a system where the poles moved into the unstable region.
And what about the zeros? We talked about the roots of the denominator being the poles. What do the roots of the numerator do?
Zeros are fascinating. While poles dictate the underlying stability and vibration, a zero acts as an anticipator of the input.
It anticipates.
Yes, because a zero mathematically introduces a derivative of the input into the system. It is essentially sensing the rate of change of the input before the full input even arrives.
It's looking at the slope.
Exactly. This drastically speeds up the response time of the system, acting almost like a predictive filter, though it can also cause a much larger initial overshoot because it reacts so aggressively.
So to recap for the listener, poles cause the system to drag, bounce, or explode, and zeros try to predict the future to speed things up.
That's a great summary.
But up until now, we've only been talking about how a system reacts to a single, sudden event, like hitting a speed bump.
Right. Isolated events.
But systems don't just experience simple, clean step inputs. In the real world, engines vibrate continuously at high RPMs, wind howls periodically, an airplane wing is constantly buffeted. We have to look at constant rhythmic noise.
We do, and that brings us naturally to how we optimize these systems in practice, using frequency response and bandwidth.
Okay, let's break down frequency response.
Frequency response is essentially asking, how does your system behave in the steady state when you feed it a continuous, never-ending sinusoidal input?
Like a constant vibration from a motor.
Exactly. What is absolutely crucial to understand here is that if your system is linear, feeling it a sine wave will result in an output that is the exact same frequency sine wave.
So if I shake it at 50 hertz.
It will shake back at 50 hertz. It will never magically output 60 hertz.
Oh, yeah.
The only things that change are the amplitude, how violent the shaking is compared to the input, and the phase angle, how delayed the shaking is.
To evaluate this, engineers use a visual tool called Bode plots, right?
Yes, Bode plots are essential here.
A Bode plot is split into two parts. On the top graph, you plot the magnitude ratio in decibels versus the logarithm of the frequency omega. On the bottom graph, you plot the phase angle delay versus the logarithm of omega.
And this step-by-step graphical optimization is where controls engineers really make their money. Dynamic systems act exactly like physical filters.
Explain that.
Think of a heavy mechanical mass. It will pass low frequencies through easily. If you push it slowly back and forth, it moves. But it will block or attenuate high frequencies.
So if you vibrate it 10,000 times a second.
Its inertia prevents it from moving at all. The threshold frequency where this blocking begins to happen defines the system's bandwidth.
And bandwidth is defined as the frequency range where the output amplitude drops no more than 3 decibels from its peak value, right?
Exactly.
So bandwidth determines the system's speed of response. A narrow bandwidth means a sluggish system that filters out all the high frequencies. It just can't react fast enough.
Right. And if you have complex periodic input noise, like a messy wind gust, engineers use a mathematical tool called a Fourier series.
What does the Fourier series do?
It breaks down that complex, messy, real-world noise into a clean stack of simple sine and cosine waves. Then they look at the Bode plot to see if those specific frequencies fall inside or outside the system's bandwidth.
But I have to ask you a serious question here because it feels like there is a trap.
There usually is.
If a wider bandwidth makes a system react faster, track inputs more accurately, and act more responsively, shouldn't we as designers always optimize for the maximum possible bandwidth? Why not make the bandwidth as wide as physically possible?
That's a very tempting thought.
Or does that just open the door for high-frequency garbage to come in and destroy the system?
That is the exact engineering trade-off, yes. An incredibly wide bandwidth means a fast, highly responsive system.
Yeah.
A fighter jet has a much wider bandwidth than a commercial airliner. But it also means you are letting in absolutely everything. You are letting in high-frequency sensor noise, electrical static, and mechanical chatter from the gears.
Oh, I see.
If your bandwidth is too wide, your control motors will try to violently react to every tiny piece of random static. The system will jitter constantly, which leads to immediate mechanical wear and tear, burned-out motors, or catastrophic instability.
So you want your bandwidth just wide enough to capture the real intended signal and narrow enough to block all the high-frequency garbage.
You nailed it.
Wow. Okay, let's take a collective breath because up to now, we have been building this beautiful, elegant mathematical castle. All of this magic in the Laplace transforms untangling the yarn, the Bode plots filtering the frequencies, the pristine state variable matrices.
It all relies entirely on one massive, incredibly dangerous assumption.
It relies on the assumption that the system is perfectly linear.
And let's be honest, engineers absolutely love to assume systems are linear because the math is easy.
It's so much easier. If it's linear and I double the input, the output doubles perfectly. If I push twice as hard, it goes twice as fast. It is a beautiful, predictable world.
But what happens when we step outside the textbook?
The superposition principle, the very bedrock of linear math, completely fails in reality.
Exactly. Superposition states that the response to a large input is exactly the same shape as the response to a small input, just scaled up proportionally. But real physical components do not work that way.
Not at all. Think about real-world nonlinearities that plague every mechanical design. First, you have dead zones.
Dead zones.
This is where a small input causes absolutely zero output. Think of a loose steering wheel in an old car. You turn the wheel a little bit left, a little bit right, and the car doesn't turn at all until the gears physically engage.
The math for a dead zone is entirely nonlinear.
Then you have backlash, where gears clack back and forth in the housing when reversing direction. And of course, you have saturation.
Saturation is everywhere. It is the reality that pushing harder doesn't give you any more output because a physical limit has been reached. A valve is already 100% open. A motor is drawing maximum current.
Assuming linearity across the board is like assuming that if you can easily lift 50 pounds at the gym, you can definitely lift 500 pounds just by trying 10 times harder.
That's a painful analogy.
The math seems right, but eventually your body hits a saturation limit, the physics completely change.
Yeah.
Your spine doesn't just scale its lifting capacity linearly, it physically breaks.
And the consequence in engineering when you ignore these nonlinearities is the creation of limit cycles.
Limit cycles, what are those?
Well, in a purely linear system, a continuous oscillation depends entirely on how hard you initially hit the system. Hit it hard, it bounces big. Hit it soft, it bounces small.
Right.
But in a nonlinear system, these limit cycles are unique, self-sustaining oscillations of a fixed amplitude and fixed period that the system will automatically fall into, completely regardless of the initial state.
Wait, explain that. It doesn't matter how hard you hit it.
Exactly. Whether you tap the system lightly or smash it with a hammer, it will eventually settle into the exact same violent hum. The system actively hunts for this specific vibration and just locks into it indefinitely.
That sounds incredibly dangerous.
It's incredibly dangerous because a limit cycle can cause metal fatigue over thousands of cycles, destroying a component that classical linear math said was perfectly stable.
So how do you actually fix this? If the linear math is broken by dead zones and saturation, and we know limit cycles are lurking in the dark, what do? We can't just throw away all the Laplace transforms and Bode plots we just talked about.
We don't throw them away. We have three primary workarounds to cheat our way through nonlinearities.
Okay, what's the first cheat?
The first is linearizing approximations. This is the most common. If we know a system is going to operate around a very specific reference trajectory, let's say we are programming a drone to hover at exactly 50 feet, we use a mathematical tool called a Taylor series expansion.
How does that help?
We use the Taylor series to pretend the system is linear, just for very small movements around that specific 50-foot hover point. It works beautifully as long as the drone doesn't deviate too far from the hover point.
But hold on, a drone doesn't just hover perfectly still in a vacuum. What if a massive gust of wind hits it, or the pilot yanks the joystick and the drone is flying wildly in aggressive banks and dives?
Well,
You can't pretend that's linear. The Taylor series hover point is useless there. We have to have a way to handle messy, high-frequency, large-scale chaos without breaking the simulation.
you're exactly right. And when the deviations are large, we move to the second fix,
Oh,
describing functions.
describe it.
This approach is incredibly clever. You take all the messy, ugly nonlinearities, the dead zones, the saturation limits, the backlash, and you mathematically aggregate them into a single comprehensive block.
So you just shove all the ugly stuff into one box.
Pretty much. Then you feed a clean sine wave into this ugly block. Naturally, the output is a distorted, messy, non-sine wave.
But here's the trick. You assume that the rest of the physical system acts as a natural low-pass filter. You assume the physical inertia of the drone will strip away all the high-frequency harmonic distortion.
Oh, wow.
So mathematically, you simply ignore the distortion and only model the fundamental base frequency that survives. It is an approximation, but it brilliantly allows you to use your standard linear frequency response tools, like the Bode plot, on a highly nonlinear system.
That is genius. You just assume reality is too sluggish to care about the high-frequency distortion, so you mathematically delete it.
Exactly.
What is the third fix?
The third fix is the phase plane method. This is a super visual approach for second-order systems. Instead of plotting a variable against time, which creates messy wave graphs, you ignore time entirely.
You ignore time.
Yes. You plot one state variable directly against another state variable.
So like plotting the physical position of a pendulum on the x-axis and the velocity of that pendulum on the y-axis, time isn't on the graph at all. Exactly. This lets you track the exact transient response graphically as a flowing path on the paper. You can literally see the system's behavioral energy drawn out as tracking spirals, saddles, and stable nodes.
What does a stable node look like?
If a system is stable and settling down, the graph will show a stable focus. It looks exactly like a spiral drawing inward, tighter and tighter, toward the dead center 0 point.
The energy is draining away into the center.
Right, and if the system is trapped in one of those dangerous limit cycles we talked about, the graph will look like a solid, bold, closed loop.
Wow.
No matter where you start on the graph, the trajectory line will get sucked into that loop and just trace it endlessly.
It's brilliant because you don't need to analytically solve the impossible differential equation. You just map where the energy is flowing visually.
Exactly.
But let's be real. Because these nonlinear equations are so incredibly horrific to solve by hand, modern engineers don't sit around drawing spirals on paper. They inevitably turn to digital simulation software. They boot up a program, build a block diagram, and hit run.
Oh yeah, they absolutely do.
And this is where the traps get truly, deeply digital. The computer takes over, and engineers blindly trust it.
Digital continuous system simulation sounds completely foolproof. The computer solves the equations over successive tiny time steps. But the massive pain point here is that engineers click simulate without having any understanding of the integration method running under the hood of the software.
And the result?
Numerical instability.
Right. The simulation literally blows up, the numbers shoot off to infinity, or much, much worse, the software spits out a beautiful, clean graph that is completely, fundamentally lying to you about reality.
To understand why the computer lies, you have to understand what the processor is actually doing when it simulates a dynamic system.
Okay, walk me through it.
The computer does not know the exact smooth curve of the real-world math. It is line to the future. It only knows the exact point it is at right now and the slope of the math at this exact millisecond, so it has to guess the next point.
And how does it guess?
The simplest, most primitive method is the Euler method. Euler calculates the mathematical slope at the current moment, draws a straight line along that slope, steps forward in time, and places the next point.
I always visualize this as walking blindfolded on a winding, curved track.
That's a good way to look at it.
You stop, you feel with your foot that the track is curving slightly to the left, so you take a perfectly straight step to the left. But because the track is continuously curving, your straight step actually takes you slightly off the track.
Exactly.
That error, the gap between your straight step and the true curve, is what we call truncation error.
That is exactly it. And with the Euler method, the truncation error is massive,
Yeah.
and it is highly sensitive to the size of the time step. If you take a giant step forward based on one quick slope reading, you will drift wildly off the curve.
So Euler is out. What do we use instead?
To fix Euler's inherent blindness, engineers developed Runge-Kutta methods. Instead of taking one blind guess and stepping forward, Runge-Kutta essentially probes the darkness ahead before committing to a step.
Probes the darkness.
The industry standard is the fourth-order Runge-Kutta method. It relies on 4 separate, complex derivative calls per single time step.
So looking ahead.
Right. It checks the slope at your current position, it calculates 2 projected slopes in the middle of the proposed step, and it checks 1 projected slope at the very end of the step. Then, it mathematically averages those 4 slopes together to create an incredibly accurate, curved path forward.
It vastly improves accuracy, but the trade-off is brutal, isn't it? It takes 4 times as much computing power to calculate a single millisecond of time.
Right, and if that is too computationally expensive, you have a third option, predictor-corrector methods, like Adams-Bashforth and Adams-Moulton.
How do those work?
Instead of probing blindly into the future with multiple slope calculations within the current step, these methods look backward. They use historical data.
Oh, okay.
They look at the past few steps the simulation has already taken to predict where the next step should naturally fall on the curve. And then they use the differential equation to correct that prediction slightly.
So it's more efficient.
It uses less processing power per step than Runge-Kutta, but requires the computer to constantly store past data in its active memory.
Okay, so let's talk step-by-step optimization. I have my software open. I understand Euler is bad and Runge-Kutta is good, but how do I choose the right step size?
That's the million-dollar question.
Because if I set my digital time step to 1 nanosecond, the straight line truncation error will be virtually 0, but the computer will take 3 continuous weeks to simulate a 1-minute drone flight.
Exactly. When choosing a step size, you're battling 2 completely opposing types of error. Truncation error, as we discussed, is caused by too large a step size. The straight lines cut the corners of the real curve, and the simulation drifts away from physical reality.
To fix it, you make the step size smaller?
But if you make it too microscopic, you run into round-off error.
What causes round-off error?
Computers only have finite decimal memory. A processor can only hold so many decimal places before it has to chop the number off.
Oh, so it just deletes the end of the fraction.
Oh, yes. When you simulate a system at a nanosecond scale, you are adding billions of microscopic numbers together over and over. Every single time the computer does the math, a tiny fraction of a decimal is rounded off and lost.
And over time.
Over billions of calculations, those tiny rounding errors accumulate, and suddenly your simulation drifts away from reality again, not because the math model was wrong, but because the computer's physical memory architecture literally corrupted the calculation.
It's a trap on both sides. Step too big, you cut corners. Step too small, the computer corrupts itself. So what on earth do you do with a stiff system?
Stiff systems.
Let's say I'm modeling a rocket engine. One part of my machine, the spark ignition and the initial chemical explosion, reacts in microseconds. But the thermal buildup, the heat soaking into the massive metal rocket nozzle, takes hours to fully develop.
A classic problem.
Do you set the step size to microseconds for the fast part and just wait a month for your computer to finish the hours-long thermal calculation?
That is the classic stiff system dilemma, and it ruins countless simulations. If you use a standard Runge-Kutta method with a step size microscopic enough to capture the ignition, you will waste endless, staggering amounts of computing power on the thermal side.
And the round-off error.
By the time you reach hour 2 of the simulation, the round-off error will have completely destroyed your thermal data.
So how do you fix it?
The fix is twofold.
Oh.
First, you use variable step methods designed specifically for stiff systems. The software dynamically changes the step size on the fly.
Oh, that's smart.
It takes microscopic, incredibly careful steps during the violent ignition event, and then, once the explosion stabilizes into a steady burn, the algorithm takes massive leaps forward in time when tracking the slow, predictable thermal buildup.
Okay, so the software adapts to the speed of the physics. What if the software can't handle it?
If the fast dynamics do not meaningfully impact the slow dynamics over the long run, meaning the microsecond spark doesn't fundamentally change the 3-hour heat soak, you simply decouple them.
You split the simulation?
Yes, You strip the high-frequency components out of the macro model entirely. You run one simulation just for the spark, take the final output of that spark, and feed it as a simple static initial condition into a completely separate long-term thermal model.
Divide and conquer.
Mhm.
Mind-blowing. As if simulation wasn't tricky enough, we finally need to close this deep dive down by answering the two most common questions engineers face today when dealing with the unpredictable reality of the physical world.
Yeah, these are the big ones.
Question one, how do we mathematically handle random, real-world noise? The wind outside does not blow in a perfect sine wave.
No, it certainly doesn't.
The electrical static in your sensor wiring is not a neat step function. Reality is chaotic.
Right. When variables contain random, unpredictable, non-deterministic components, we are officially dealing with stochastic systems.
And how do we model those?
To model stochastic systems, engineers have to completely abandon their deterministic differential equations. You can't rug an exact equation for a gust of wind. Instead, we turn to probability density functions, specifically the zero-mean Gaussian distribution.
The classic bell curve.
Exactly. The absolute magic of a Gaussian or normal distribution is that it can be completely specified by just its variance, its spread. And if you feed a purely Gaussian noise input into a linear system, the output is mathematically guaranteed to also be perfectly Gaussian.
Oh, so it preserves its shape.
Yes, it makes the math incredibly predictable even when the input is chaotic.
But how do you know if the noise from 1 second ago affects the noise right now? Wind isn't purely random. A gust right now usually means it will still be gusting a half second from now.
For that, you use the autocorrelation function. This is a measure of time correlation. It tells you exactly how strongly past values of the random noise affect future values.
Okay, give me an example.
If the noise is purely random white noise, like TV static, the autocorrelation is zero everywhere except at the exact present moment. The past does not dictate the future. But if the noise is a rolling wind gust, the autocorrelation will show a distinct sloping curve.
And what do you do with that curve?
You pair this autocorrelation data with power spectrum filtering to figure out exactly which frequencies of the random noise possess the most physical energy, so you can specifically design your drone's software filter to ignore them.
Which perfectly tees up question two. How do we actually integrate these continuous analog physical systems with modern digital computer processors?
A huge challenge today.
Because computers don't think in continuous time. A computer processor thinks in discrete digital ticks. It pulses.
This brings us to discrete and hybrid systems. To get continuous real-world data like the pressure in a pipe into a digital computer, you must use uniform sampling.
Okay, so sampling at regular intervals.
Yes. You tell the sensor to sample the physical variable at a set interval, say every 1 millisecond. But you must obey the fundamental law of digital conversion. The sampling theorem, also known widely as the Nyquist criterion.
The Nyquist criterion, what is the rule?
The sampling period must be mathematically fast enough, specifically greater than twice the highest frequency present in the signal to capture the true physical movement. If you sample too slowly, you get a catastrophic error called aliasing.
You know, aliasing is so easy to visualize. It is exactly like when you watch a car commercial on TV and the car is driving forward on the highway, but the wheels look like they are spinning backward.
Yes, the camera frame rate effect.
The camera's frame rate, which is its sample rate, isn't fast enough to catch the true continuous rotation of the wheel. It only captures fragmented snapshots that trick the brain into seeing reverse motion. If your drone's altimeter aliases a vibration, the computer might think the drone is falling when it's actually rising. The data is completely corrupted.
Exactly. So that gets data into the computer safely. But to output data from the digital computer back out to the physical motors, we use something called a zero-order hold.
A zero-order hold.
Because the computer only spits out control commands at discrete intervals, say one command every 10 milliseconds. The zero-order hold takes that discrete number and holds the physical voltage to the motor absolutely constant until the very next digital number arrives.
So it's not a smooth curve anymore.
No, it creates a rigid staircase pattern of voltage inputs for the analog system to react to.
A zero-order hold is literally a strobe light in a dark room. It freezes continuous fluid motion into distinct, separate, rigid steps that a digital computer can actually comprehend and control.
That is a brilliant way to put it. And to handle the mathematics of these discrete staircase steps, we cannot use the continuous Laplace transform we talked about earlier.
The Laplace math only works on continuous yarn.
Exactly. For digital steps, we introduced the Z-transform. The Z-transform does for discrete digital systems exactly what the Laplace transform does for continuous analog ones.
So it dissolves the digital knots.
Right. It takes discrete difference equations and turns them into manageable algebra, allowing us to build pulse transfer functions to perfectly control complex computer-driven robotics.
Wow. That is an absolutely incredible amount of ground covered today. Think about what we just did.
We covered a lot.
We took a chaotic physical system, we idealized it into universal T, A, and D components. We mapped the energy flow using state variable matrices. We untangled the math by bringing it into the time and frequency domains using Laplace transforms and Bode plots.
We shattered the dangerous illusion of linearity.
We navigated the hidden integration traps of computer simulation, and finally, we bridged the gap between the continuous analog world and the discrete digital brain using the Z-transform.
It is the complete, holistic life cycle of dynamic system modeling. But as our digital computers get exponentially faster, as our Z transforms and our fourth-order Runge-Kutta algorithms get more impossibly precise, and as artificial intelligence begins to actually automate the formulation of these very state matrices for us, it leaves us with a truly provocative thought about the future of engineering.
Oh, what's that?
Will we eventually hit a point in our lifetimes where our mathematical models achieve such perfect, godlike fidelity that physical prototypes become entirely obsolete? Or will the stochastic chaos of the real world, the unpredictable friction, the uneven heat gradients, and the stubborn random noise of reality always demand that an engineer eventually has to put down the simulation, build the physical thing, turn it on, and watch it break?
Man, a terrifying and strangely beautiful thought to leave off on. You can't truly simulate reality until you truly understand it, and maybe reality always has one last unpredictable trick up its sleeve. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.